Alright, let's go. Number 10. The positron excess. In 2006, a joint Italian-Russian collaboration bolted a magnetic spectrometer to the side of a Russian Earth observation satellite called Resurs DK1 and launched it into a polar orbit. The instrument was named Pamela. Its assignment was unglamorous: measure the ordinary background of cosmic ray particles hitting the upper atmosphere. Build a clean baseline catalog and hand that catalog to the dark matter community so they would know what normal looked like. Bookkeeping, nothing more. Normal was well defined. Positrons, the antimatter twin of the electron, are not supposed to be produced in bulk anywhere near us. They arise as debris when a fast cosmic ray proton slams into a hydrogen atom in interstellar gas and sprays out pions that decay. Debris production falls off with energy. Every model agreed the fraction of positrons in the cosmic ray flux should decline smoothly and monotonically as you climb the energy scale. Above 10 billion electron volts, the fraction stopped falling. It climbed. Oscar Adriani and the Pamela collaboration published the result in Nature in 2009, covering the range from 1.5 to 100 billion electron volts. 4 years later, the Alpha Magnetic Spectrometer mounted on the International Space Station, led by Samuel Ting of MIT, confirmed it with 6.8 million events in physical review letters. The positron fraction rises from roughly 8 billion electron volts and does not turn over until somewhere near 275 billion. Explanations arrived quickly and died slowly. Dark matter annihilation fit the shape, but required an enhancement factor of several hundred over the natural rate, and produced no matching excess in antiprotons. Nearby pulsars, Geminga and Monogem, became the consensus fallback, until the Hawk Observatory measured the gamma-ray halos around both in science in 2017 and found particles diffusing roughly 100 times more slowly than that model needs. Secondary acceleration inside supernova remnants predicted a hardening in the boron-to-carbon ratio that the data has not delivered. Something within a few hundred parsecs of your house is manufacturing antimatter continuously, and it has been doing so for the entire history of your species. We have measured its output for 17 years without once identifying the source. That is the cheapest antimatter in the universe. Ours costs more. Number 9. The production cost wall. CERN did not set out to price antimatter. The antiproton decelerator was built in the late 1990s for a narrow physics purpose: slow down antiprotons enough to trap them, so that spectroscopists could measure antihydrogen and compare it to hydrogen. The economics were a byproduct, an accounting detail that emerged only when engineers tallied how much beam time and electrical power each captured antiproton had cost. The theory says antimatter should be easy in one sense. Energy converts to matter-antimatter pairs whenever you exceed the mass threshold. Slam protons into a fixed target at sufficient energy, and antiprotons appear as a matter of routine. There is no exotic barrier. It is standard particle physics, performed daily since the 1950s. The yield is the problem. Almost none of the input energy ends up in the product. Roughly 1 antiproton emerges usable per million protons fired at the target, and the capture and cooling stages discard most of what survives. CERN's own published estimate puts total antiproton production across its entire operating history at well under 20 nanograms. NASA's frequently cited figure for scaling this to 1 gram of antihydrogen is approximately $62.5 trillion, larger than the annual economic output of the planet. Every proposed shortcut has stalled. Higher energy collisions raise gross yield but lower capture efficiency because the products come out faster and harder to trap. Dedicated production rings, studied by Gerald Jackson and Stephen Howe under NASA's Institute for Advanced Concepts, improve efficiency by perhaps a factor of 10,000 and remain a factor of 1 billion short of practical. Harvesting natural antiprotons from Earth's inner radiation belt detected by the Pamela team in 2011. Yields a standing population measured in nanograms across the entire magnetosphere. The most energy-dense substance permitted by physics exists. It is manufacturable, and the entire industrial capacity of civilization has produced less of it than the weight of a single grain of sand. What does it mean that the universe made kilograms of this in its first microsecond effortlessly, and we cannot make a speck? The reason we keep trying is what happens when the speck touches anything. Number 8. The Annihilation Ledger. The number that made antimatter famous came out of a routine calculation. In the 1930s, after Carl Anderson confirmed the positron and cloud chamber tracks, theorists worked through the obvious consequence. What happens to the mass when a particle meets its antiparticle? The arithmetic was elementary. They were not searching for a weapon or a rocket. They were closing a loop in conservation bookkeeping. Einstein's relation gives the answer directly. Total mass converts to energy with no residue. 1 kilogram of matter meeting 1 kilogram of antimatter releases about 1.8 times 10 to the 17th joules, roughly 43 megatons. Comparable to the largest thermonuclear device ever detonated. Fission converts about 0.1% of its fuel mass. Fusion, about 0.7%. Annihilation converts 100%. Except the ledger does not balance when you ask where the energy goes. Proton-antiproton annihilation does not produce a clean flash. It produces pions, on average around 3 charged and 2 neutral. The neutral pions decay almost instantly into gamma rays, which are usable. The charged pions decay into muons and neutrinos, and the muons decay again into more neutrinos. Neutrinos interact with essentially nothing. Somewhere near half the released energy walks out through the walls of any conceivable container and keeps going. Engineering fixes have all failed on the same physics. Magnetic containment of the charged pions extends their path but cannot stop the decay chain, which is governed by the weak interaction and indifferent to field strength. Using positrons instead of antiprotons yields clean 511 kilo-electron-volt gamma rays with no neutrino loss. But positrons carry a 2,000th of the mass energy per particle. Absorbing the gammas requires shielding, whose mass defeats the purpose. The most efficient reaction available in this universe leaks half its output into a form of radiation that passes through planets, and there is no known material or field that can catch it. If the perfect fuel is unburnable, what exactly did the early universe do with all of it? That question has an answer, and the answer is a hole in the record. Number 7. The alpha-G result. Jeffrey Hangst and the Alpha collaboration at CERN spent 2 decades building an apparatus to hold antihydrogen still. The scientific goal was spectroscopy, shine a laser at trapped antihydrogen. Measure the frequency at which it absorbs, compare the number to hydrogen. Gravity was a side question, an experiment of opportunity, made possible only because their magnetic trap could be opened from the top or the bottom. Every relativistic theory demands one outcome. General relativity does not distinguish sources of mass energy. The equivalence principle applies to antimatter without exception. Antihydrogen must fall down at exactly the same rate as hydrogen. A small community had argued otherwise for 40 years, because anti-gravity would elegantly explain why matter and antimatter separated in the early universe. They released the atoms and counted where they annihilated. The atoms fell down. The result appeared in Nature in September 2023 under Anderson and the Alpha collaboration. Antihydrogen fell with an acceleration measured at 0.75 times local gravity, with a combined uncertainty of about 0.13, consistent with 1, and excluding repulsive gravity outright. That closed one door and opened a worse one. Antigravity had been the last elegant explanation for the missing antimatter. And it is gone. Meanwhile, the precision achieved is roughly 13%. Torsion balance experiments at the University of Washington test the equivalence principle for ordinary matter to a few parts in 10 to the 13th. A violation for antimatter anywhere below the 10% level would still be invisible to us. Proposed follow-ups using antihydrogen interferometry remain years away, and the muonium and positronium alternatives suffer from lifetimes measured in microseconds. The single most promising explanation for why you exist has been eliminated, and the experiment that eliminated it is 100 billion times less sensitive than the equivalent test on ordinary matter. How confident should anyone be in a null result measured to one significant figure? If antimatter is not hiding in the direction of gravity, it should be hiding somewhere in the sky. Number 6. The anti-helium candidates. The Alpha Magnetic Spectrometer was installed on the International Space Station in May 2011 with a specific mandate from Samuel Ting: count cosmic ray nuclei with enough statistics and enough rigidity resolution to settle questions that balloon flights could only gesture at. Identifying anti-nuclei was on the list, but nobody expected the list item to activate. It was included for completeness. Antihelium is the cleanest possible signature of primordial antimatter. Ordinary cosmic ray collisions can manufacture antiprotons easily and antideuterons rarely. Assembling a full antihelium-4 nucleus from collision debris requires 4 antinucleons to emerge with nearly identical momenta, and the estimated probability is suppressed by something on the order of 10 to the minus 17. Detection would mean the nucleus was made somewhere, in bulk. Between 2018 and 2021, Ting reported in conference presentations a small number of candidate events, roughly 6 consistent with antihelium-3 and 2 with antihelium-4. The collaboration has not published these as a detection in a refereed journal. The reason is that the alternative explanation is mundane and hard to exclude: an ordinary helium nucleus whose charge sign is misassigned because of a rare tracker mismeasurement. The Bess Polar 2 Balloon Experiment, published by Abe and colleagues in Physical Review Letters in 2012, set an upper limit on the antihelium to helium ratio of about 6.9 times 10 to the minus 8 and saw nothing. Every proposed source has failed independently. Dark matter models cannot produce antihelium-4 at observable rates without violating antiproton limits. Nearby antistars would betray themselves in gamma rays. Statistical fluctuation cannot be ruled out at these event counts, and will not be for years. 8 particles, arriving over a decade, either constitute evidence that an entire region of the universe is built from the opposite of you, or they are a tracker glitch. 15 years of data have not been enough to tell the difference. The wider search for whole galaxies of it went worse. Number 5. The Domain Boundary Limit. Andrew Cohen, Alvaro Di Riula, and Sheldon Glashow set out in the mid-1990s to be generous to a hypothesis they suspected was wrong. The idea was old and appealing. The universe contains equal matter and antimatter, separated into vast domains, and we simply happen to live inside a matter one. Their paper was intended as a fair test of how large those domains would have to be to remain hidden. The physics of the boundary decides everything. Intergalactic space is not empty. Wherever a matter domain touches an antimatter domain, gas from each side meets and annihilates, and proton-antiproton annihilation produces neutral pions, which decay into gamma rays at a characteristic energy near 100 million electron volts. Boundaries glow. They compared the predicted glow to the measured diffuse gamma ray background. Nothing matched. The result was published in the Astrophysical Journal in 1998. To stay below the observed background, the nearest matter-antimatter boundary must lie at least a gigaparsec away, around 3 billion light-years, comparable to the scale of the observable universe itself. Any domain structure must be at minimum the size of everything we can see, the escape routes closed one by one. Voids between domains were proposed to suppress annihilation, but gravity refuses to hold a vacuum open at those scales during structure formation. Magnetic separation fails because the required field strengths exceed observational limits by orders of magnitude. Inflation can stretch domains to the necessary size, but only by requiring the asymmetry to be set before inflation, which reintroduces the original problem in a less testable form. Cluster gas surveys, including X-ray measurements of the Perseus and Virgo clusters, show no annihilation signature anywhere within them. Every atom in your body belongs to a majority that appears to have no minority. Out to the furthest distance light has had time to travel. If the antimatter is not near us and not far from us, in what sense was it ever here? The symmetry that says it must have been here is the most tested statement in physics. Number 4. The CP constraint. Gerhard Elders and Wolfgang Pauli were not investigating antimatter shortages in the early 1950s. They were examining the formal structure of quantum field theory, asking which transformations must leave the equations unchanged if the theory is to remain consistent with relativity and causality. The answer fell out as a theorem rather than a hypothesis. The CPT theorem states that any local Lorentz invariant quantum field theory is exactly symmetric under the combined operation of reversing charge, reflecting space, and reversing time. It is not an assumption anyone chose. It is a consequence. Break it. And either relativity fails or causality fails. The theorem implies that a particle and its antiparticle must have identical mass, identical lifetime, and exactly opposite charge and magnetic moment. Physicists have spent 70 years attacking it, because a violation would explain everything, and it has never bent. The numbers are relentless. The base collaboration at CERN, led by Stefan Ulmer, compared the proton and antiproton charge to mass ratio to 16 parts per trillion, published by Borchert and colleagues in Nature in 2022. The alpha collaboration measured the 1s-2s transition in antihydrogen and found agreement with hydrogen to about 2 parts in 10 to the 12th in Nature in 2018. The neutral kaon system constrains any mass difference between the kaon and its antiparticle to below 10 to the minus 18 of the kaon mass, the most precise equality ever established between two physical quantities. Every attempt to build a loophole has cost more than it bought. Non-local theories break causality. Lorentz violating extensions, cataloged in the Standard Model Extension Framework of Alan Kostelek, are tightly bounded by every experiment above and by astrophysical timing. String-inspired models push violation to the Planck scale, where nothing is measurable. Matter and antimatter are, as far as any instrument on Earth can determine, exactly equal and opposite. And yet you are made of one and not the other. What broke a symmetry that appears mathematically unbreakable? There is one crack in it. The crack is far too small. Number 3. The CP shortfall. James Cronin and Val Fitch went to Brookhaven in 1964 to do a confirmation experiment. Neutral kaons were believed to respect CP symmetry, and the long-lived kaon was therefore forbidden from decaying into two pions. Their beamline was designed to verify the prohibition and quantify the detector's precision. It was, in the language of the time, a clean-up measurement. CP symmetry says that if you swap every particle for its antiparticle and mirror reflect the result, physics runs identically. Every experiment before 1964 had supported it. Andrei Sakharov would show 3 years later, in a 1967 paper in JEP Letters, that any universe made predominantly of matter requires CP violation, along with baryon number violation and a departure from thermal equilibrium. Without all three, matter and antimatter annihilate to nothing. Cronin and Fitch found the forbidden decay. It occurred in about 2 events per 1,000. Makoto Kobayashi and Toshihide Masukawa built the effect into the Standard Model in 1973 in Progress of Theoretical Physics, requiring a 3rd generation of quarks to accommodate it. The resulting quantity that measures the strength of CP violation, the Yarlskog invariant, has magnitude around 3 times 10 to the minus 5th. Carried through to a prediction for the surviving matter density, the Standard Model yields an asymmetry near 10 to the minus 18. The observed value is 6 times 10 to the minus 10. The shortfall is 8 orders of magnitude. Additional sources have been hunted and have not closed the gap. LHCb confirmed CP violation in charm mesons in 2019 at roughly 1. 5 parts per 1,000. The right sign, the wrong scale. T2K reported hints in neutrino oscillations in Nature in 2020, still short of discovery significance and still insufficient. Worse, Kajanti, Laney, Rumokainen, and Shaposhnikov showed in Physical Review Letters in 1996 that with a Higgs boson as heavy as the one found in 2012, the electroweak transition is a smooth crossover, which destroys Sakharov's 3rd condition entirely. The mechanism responsible for your existence is not merely unknown. The known mechanism has been measured and found to be 1 billion times too weak. If the Standard Model is right, you should not be reading this. Which brings us to the number that survives every attempt to explain it away. Number 2, the baryon asymmetry. The number came out of cosmology, not particle physics. In the 1960s and 70s, theorists working on Big Bang nucleosynthesis were calculating how much helium, deuterium, and lithium the first 3 minutes should produce. The ratio of baryons to photons was an input parameter they needed to pin down. They were fitting light element abundances, not investigating antimatter. The early universe was hot enough that photons routinely produced particle-antiparticle pairs, and pairs routinely annihilated back into photons. Symmetric production means symmetric outcome. As the universe cooled below the pair production threshold, everything should have annihilated, leaving a universe of radiation and essentially nothing else. No atoms, no stars, no chemistry. The nucleosynthesis fit returned a non-zero number, and the CMB later confirmed it independently. Planck's 2018 measurement of the acoustic peaks gives a baryon-to-photon ratio of about 6.1 times 10 to the minus 10th, in agreement with the deuterium abundance derived from quasar absorption spectra from completely separate physics. That number means that for every billion antiquarks in the early universe, there were 1,000,000,001 quarks. Everything that exists is the residue of that single excess part per billion. Nothing has explained the one. Grand unified baryogenesis predicts proton decay, and Super Kamiokande has pushed the proton lifetime beyond 10 to the 34th years without seeing a single event. Electroweak baryogenesis needs a first-order phase transition the measured Higgs mass forbids. Leptogenesis, via heavy right-handed neutrinos, remains viable and remains untestable. The required masses sit near 10 to the 14th electron volts, 14 orders of magnitude above anything the LHC can reach. Affleck-Dine baryogenesis works but requires supersymmetric fields no experiment has detected. Every atom in your hand, in your food, in the star that made your carbon is a leftover from an annihilation event that consumed 1,000,000,000 times more material than it spared. Why 1? Why not 0? The last item does not answer that. It suggests the question may be badly posed. Number 1. The backward clock. In the winter of 1940, John Wheeler telephoned his graduate student Richard Feynman with a proposition. Feynman was working on the problem of electron self-energy, an infinity in the equations that no one could remove. Wheeler was not addressing that problem. He said he understood why all electrons have the same mass. There is only one electron. Threading forward and backward through time, and every backward pass is what we call a positron. The mathematics beneath the joke is standard. Ernst Stuckelberg proposed in 1941, and Feynman formalized in Physical Review in 1949, that a positron is described by exactly the same equation as an electron with the sign of time reversed. In every Feynman diagram used in every calculation since, antiparticle lines are drawn as arrows pointing backward. This is not interpretation, it is how the arithmetic is performed. Nobody has ever found a way to distinguish that description from the conventional one experimentally. The predictions are identical to every decimal place measured. The electron magnetic moment agrees with quantum electrodynamics to 12 significant figures using backward pointing lines. Meanwhile, direct time reversal violation has been observed. The Pleer collaboration reported it in the Kaon system in Physics Letters B in 1998, and the Baybar collaboration measured it directly in B mesons at 14 standard deviations in Physical Review Letters in 2012. Time is not symmetric at the particle level. The obvious objection to the one-electron universe is that the sky is not half positrons, and no one has explained why not, which is the baryon asymmetry problem again, wearing different clothes. Attempts to make the time reversal reading physically meaningful rather than merely formal have produced transactional and two-state vector interpretations, none of which has generated a testable prediction distinguishing it from the standard account in over 60 years. The particles you are made of are described in the working equations of physics as being accompanied by identical particles traveling backward through your past. If the mathematics cannot tell those two stories apart, on what grounds do you believe you are moving forward? 10 entries, and not one of them sits at the frontier. The positron excess was found by an instrument built to measure backgrounds. The CP shortfall lives inside the standard model, the most precisely verified theory ever constructed. The baryon asymmetry is measured to 2 decimal places by 2 independent methods that agree. These are not gaps at the edge of knowledge. They are holes at the center, load-bearing and unfilled. And we have built everything on top of them anyway. The universe is not confused about why it contains matter. Only we are. You are the surviving 1 in a billion, and nobody can tell you why you were spared. If you want to see more videos like this, click the video on screen now.